Hello, welcome back to Design a Computer from Scratch. In part 3, we'll start into the design, and the element we're going to design first is the program counter. It's fairly simple, but it will illustrate the other design element operations, how we work with Quartus to design VHDL code. In part 1, we already created a simple entity which just had the LED and a switch, and you could press a button and light the light. It wired the switch straight through to the light. In this part, LED, in this part we will actually make a program counter and do some testing. It's always good to do some testing. The program counter details, if you remember from the previous part 2, is a 12-bit program counter. It loads 0, 0, 0. It's a 12-bit address, so it's 3 nibbles of 0 at reset. And it requires control signals to increment the counter. Since we have multiple clocks per instruction, 4 clocks per instruction, we only want to increment on one of those 4 clocks. Everything should be synchronous to that 50 megahertz clock, and strobes are created for increments. And also we want a strobe for load when you do a branch or jump instruction. And we determined or decided that the branches are going to use an absolute address, so we don't need to do any relative branching. The full 12-bit address will be inside of the bottom 12 bits of the instruction, so we don't have to do any math on the current address and the branch, which you would have to do if it was a smaller branch. It's just a simplifying assumption that is easy to support in this architecture. We've already created a top-level entity, and currently it just wires directly through, but for the sake of ease, we will just copy that top-level entity into a program counter element. So the way we'll do that is to clone it, just copy the contents, and then we'll change it here and there to make it into a program counter. Inside of Quartus, there's a couple of views that are you bounce back and forth between quite a bit, and it's found here in Quartus 20 version 20 under the project navigator, and either select files or select hierarchy. In this case we're going to create a program counter.vhd, but if we do file new, it will create a file with some other sort of a name, and we'll have to rename it as program counter. So do file new to select, and then the list will pop up and make a VHDL file, and we're going to want to save it as programcounter.vhd. We're going to want to make sure that we're in the same folder, that there's no path displayed here. We want everything to be in the same location as the CPU itself. And if you click that files button, if it was in hierarchy, you have to change to files to see those files. And what we'll do next is copy the contents of the CPU 001 that we created in part 1, and we're going to paste it into the program counter. And notice it's still got the same things that it had. We'll have to go change some things. We don't want to have a port that has a key and a light LED on it. We want to have the port be correct. We'll change those entity port pin names, and we'll have different wires for the behavior or the signals here, and of course the logical change. But if we start from the one that we've already made successfully, was able to compile, we're able to compile it, it'll be a lot easier because we won't have the typos that we would normally have. So we'll replace those pins with the new pins. So we're going to search the file for that CPU 001, which was in the entity, and do a replace all. Remember, it occurs in 3 places. It occurs in the entity, the end of the entity, and then further down. So it should make 3 changes. That's the first thing we really have to do to make this callable from the CPU 001, is to change that entity name. And I prefer to have the file name match the entity name. It just makes it easier to work with. It's not necessary, but we will follow that convention for almost everything we'll do. There'll be one or two things that don't follow that, but it's just much easier. Not necessary, but easier. So what signals do we need for a program counter? Well, we need the clock, and so far we don't have a clock, so at the CPU 001 level, we'll have to add that clock in to be able to push it down into the program counter. But for now, we'll just pretend like we have it, and we'll add that as an in. It's a 50 megahertz clock. And we're going to again follow NANLAN's convention of do I underscore at the beginning for input pins, O underscore at the beginning of the name of the pin for output pins. And that clock is a single standard logic type. It's a 1 or 0, and that's what that indicates when you say standard logic. So clock, load PC to be able to load the program counter. We need a strobe to be able to increment the program counter. And that's those are all three in standard logics. They're single bits. But when it comes down to the load value, if we want to do a load, we have to have those 12 bits available. So we'll call that program counter load value, and it'll be this IPCLD VALR, and it's an in as well. But because it's more than one bit, it's a standard logic vector, and the size has to be indicated, and that's 11 down to 0. This could be any index range, but the bigger number down to the smaller number, and it's convention to make the bottom number 0, so we'll follow that convention by and large. And a program counter output would be similarly, it would say out, and then standard logic vector to say that it's a number of bits. 11 down to 0, so 12-bit input load value, 12-bit output counter. Open question here is, do we need to have a reset in here? At the moment we don't, and I believe that the FPGA initializes registers to 0 when it comes on, so it'll come up and start running at 0. If you want to start somewhere else, just do a jump to wherever you want it jump to, but for a simple controller like this, always starting at 0 is a good simplifying assumption. It just makes things a lot easier. And of course, again, we're bounded in the entity. Program counter is defined as these pins, and the end will have that program counter as well. We need a single signal that is the program counter itself. I believe this gets changed as we go along here to be a standard logic vector as well. It doesn't have direction because it's just a wire, and wires don't have directions. But that gets placed after the end from the previous step and below the architecture, but before the beginning of the block itself. Well, we're calling the architecture BEH, like behavior, but again, it could be Uncle Fred. It doesn't really matter. And that same program counter, her name appears here. Those three have to match: the beginning of the entity, the end of the entity, and the beginning of the architecture. The program counter is going to be a clocked element, so it's going to use one of these sort of process blocks. And the sensitivity list is the things that change inside of the block or would cause change. And in this case, it's only the clock that would cause a change. The section inside of the process has a begin and end, and there's an end process that matches the begin up here. And inside of it, you can do ifs and else's, but make sure you always match end ifs when you're done. So the if for the rising edge of the clock is matched with the end if here, and the if for this if, else if, end if loop is here. Syntax is, or typing is very important here in the strict checking of VHDL compiler, so it has to be ELSIF. It can't be ELESEIF or something like that. The compiler will throw up an error and you'll have to go correct it. What's this function doing? Well, this function is loading the program counter with that load value that we had in our pin list. When the load PC input strobe is high, or it's incrementing that counter when the increment PC strobe is high. And the way it's set up here is there's a priority in essence. If load is present, then it will ignore the increment and it'll do the load. If load is not present, then it will do the increment. And that will provide a helpful simplifying assumption. We can always hit increment even if we really don't intend to increment, because it will be ignored if the load value is present. So if load is low, it's not loading, then it will fall through to this increment. And that's really all it takes to make a counter. The part here is the W program counter gets loaded. That's the wire for that program counter. It's loaded with count +1. And that was defined externally as a signal, and it should have been standard logic vector with 11 down to 0. And outside of that, we're going to take those bits and we're going to take the output program counter and make it be the value that's inside the loop here. Again, load will take priority over the increment. So we'll need to add that clock that we added inside of the PC itself. We need to add that to the top level entity pins. We already had a key 0 input and an LED output. We'll add the iClock as an in, and it's that 50 megahertz FPGA clock. It's on one of the pins. We'll find it from the schematic like we did for the key and the LED. And it still has these same 3 CPU 001. This is the higher level entity. And this gets connected when we add the entity into the CPU of the program counter. It will get connected down in. So let's add that program counter into the top. So basically what I like to do is to copy from the entity itself and paste it into the file. Add a little comment here saying this is the program counter. That's the dash as comments, and shove it in there. But we're going to get rid of most of the stuff to the right here, but at least gets us in the right direction. We aren't going to want to copy the end program counter because that's not needed when you instantiate it in the CPU 001, but we'll just start out copying that and we'll paste it into the top section here. There's a few things we have to add. We have to add this prog counter, the label, to tell it what this entity's name is, and a colon between that and the entity that we already had. And we have to add that work, which says, hey, pull that out of somewhere else. It's not inside of this file. And port was in there before when we copy pasted it, but the word map wasn't, so we have to put in the map, and that's telling how those pins are mapped. And the mapping is essentially saying, hey, the entity calls it iClock, but I want to call it iClock. Well, in this case, they're the same. All of these are the same, and we're keeping them the same, but the difference, if you note, coming into the entity, it's iClock, but inside of here, it's normally, well, it's still iClock because it actually comes from an outside pin, but LoadPC is a wire that's inside of the top, and we've already called it iLoadPC inside of the entity, but it's WLoadPC here inside of the top level. And this is the mapping of those entity pins to the signals or pins that are inside of that entity that it's instantiated in. And we're going to hook it up inside of the next couple of steps here. So VHDL has differences. The way we're dealing with that is when we copy paste it, we just basically get rid of what was there and put it in that mapping thing, the equals, right arrow, space, and a comma. Note, syntax wise, there's no comma on the last one in the entity instantiation in the top level. It's left blank. If you put a comma there, it would look for another element. So yet another thing the compiler will cause an error, and that error might be farther down. It might tell you, hey, something down here is wrong. Well, it was up here. It didn't close it out. So not putting a comma there allows it to detect that it's done. The parentheses sort of do that too, but again, very strict checking inside of VHDL, and you have to have it just right. We'll throw comments in here as we go along just to make it obvious what these things are. Not only are they commented in the entity itself, but we'll comment them oftentimes where they're called from just to keep track of what it is. For now, we'll just leave things the way they are. We haven't created these wires. We showed what they'd be like in the previous screen, but this is how it'd be after you copy paste it and then do some trimming on it. The only external pin we have is that I clock, so we filled that value in, and the rest are all going to be signals that are inside of the entity itself that's calling the other entity. So we need to add those signals to the top of the CPU 001, and that's LoadPC, and that's standard logic of a default value for now. If you do the colon equals and then the single quote, zero single quote, again, these will all have semicolons in the end, but that'll set the default value if we haven't assigned it in the function itself to 0. So we're not going to load the PC. We're not going to increment the PC. That's what we want our default values to be. Some function will do that, but this will override it if there's no function, or not override, but it'll set the value if there's no function that sets it. If something sets it, then it ignores what it sees inside of here because it's set down in the code farther down. For now, we'll just throw a PC load value of 123 in there. We're not going to do anything with it, but we're just setting it as a blank value. And there's really no point in setting a default value for wprog counter because we are creating prog counter and that will exist. So that will always come out of the program counter element, so we don't set a default value for that. So here's the signals. I gave a preview of it in a couple of slides previous, but the I clock will go to the I clock, which is the CPU's clock or the FPGA's clock pin, and the rest all go to a W wire version of those signals. This could be called anything. This could say I LoadPC has to match the entity, but this could be called W Uncle Fred's PC incrementer or loader or something like that. It could be called anything we want to call these things. But if we call them something very similar and we've made our signal name smart, it'll be easy to tell what it is, won't need a lot of comments. Now there's guaranteed to be typos, and there was an error in what we did. I think I mentioned one of them, maybe you spotted other ones, but how would we test this function? Well, the first thing we can do is we can just compile everything, and when we compile it'll tell us if there's any compile errors. But if this was a Ben Eater video, he would just throw a 555 on it, crank it down to a slow speed, and look at it to see if the address lines are changing with a bunch of LEDs. This is a much more powerful tool than LEDs, and we could use a tool called Signal Tap, but we'll ignore that for the moment because it's just a little too advanced. We will use it when it comes to looking at things that are more complicated. At the moment, we're going to ignore it. It's pretty easy to use. It's like having a very expensive logic analyzer inside of the FPGA, but at the moment we'll just ignore it. Or maybe we could just use the push button and LED to do something. I think Ben would do something like that. I'm sort of following in his inspiration here. With the difference being the goal here is producing something useful. It's less impressive to your friends because it's not a table full of breadboards, but you know what's going on inside of here. It's a fully functional CPU that's useful definitely for I/O processing type of functions. But for this example, we could use the push button and the LED to do something. Let's think about what we can do. Well, the one thing we do note when we go to compile is that it will complain, and it complained inside of the program counter because it doesn't know how to do that +1 because we didn't have in our boilerplate any arithmetic. So let's throw these two lines in here. We'll just sort of treat all these things as library boilerplates, but it's the IEEE standard logic arithmetic element and the unsigned math arithmetic. That's really what we want to be able to do, the math for that counter. Those IEEE libraries help us make sense out of things like standard logic and standard logic vector. That's what interprets those and does something with those. If we want to do what Ben was doing, we could make a slow clock. We don't need to run a 555 into this. So if we took that 50 megahertz clock, but we ran that into the PC, well, 50 million divided by 4096 is still pretty darn fast. It's too fast. The light would be too fast to see. But how about if we make our own slow clock? We could use that similar to the way that Ben's using the slow clock and Others would use a slow clock to test the program counter. And it should be easy enough. After all, we just made a counter. We know how to make counters. Let's just throw that counter at the top for the moment. And if the CPU or the FPGA's 20 nanosecond 50 megahertz clock, we want to get that somewhere down around 10 hertz. You can see 10 hertz. It's a fast blink, but you can definitely see it. So if we took 50 million and divide by 10 hertz, that's a 5 million count. But let's pick the nearest power of 2 just to make our counting simple. 2 to the 22nd is 4 million. So if we had a 22-bit counter, we get something around 12 hertz, which is definitely visible. And if we run a 12 hertz counter into our program counter and then we tap into the program counter bits with our LED, we should be able to see that flash. Making the slow clock, we did need to find this pin anyway. It's from the schematic. The signal name for the 50 megahertz oscillators clock underscore 50M, and it's on pin T2 of the FPGA. So we'll need that. We'll add that to the pin list just like we did in part 1. If you didn't watch part 1 on how to add pins to assign pins to the part, it's a good thing to do. So we did that, and it worked. And what did we have to add? Well, we had to add set of wires for slow clock count to our entity, or to our CPU underscore 001, and that's standard logic vector with 22 bits, which count from 21 down to 0. And we had to make that counter itself. It's a real simple loop, very similar to the program counter with no load, and it just always increments. So it's the same sort of a process loop with we called it slow clock. And on the rising edge of that input clock, that 50 megahertz clock, increment slow clock, and that would end it. If we pick off the LED, I think it's actually going to be faster than that, because I think it'll be 22. It'll be 24 hertz still. Again, you can see it blink. It's good enough to drive it. If you have it too small not enough bits of a counter, it'll go too fast. If you have too many, it'll count too slow to pick them off. So basically, we can send this clock out to the LED and watch it blink, and it's visible, so we know that it worked. Now we want to turn that clock into a single pulse, single 20 nanosecond pulse that occurs at that clock rate. And if we look at the edge detect is finding where a transition changed. This is a very classic edge detect sort of a circuit. It has a clock process for that slow clock that has that counter inside of it from the previous step, but we've added into it something to delay by 1 clock when that 21st bit gets set, and then something to delay that again by that. And if we take has the first one arrived but the second edge not arrived, that will produce out a single pulse that is every 12 hertz, and that's a real nice clock rate to do what we want to do. So that's really all we had to do to add that entity, or that function, excuse me, it's not an entity yet, just add that function into CPU 001, and we've got our own little 555 equivalent. So let's take that slow pulse and use that as our increment, the program counter, and then pick off a bit of that program counter and send it out to the LED. And when we run that, it blinks at a nice little rate. And if we pick a higher bit, instead of 0, let's pick the third bit up, bit 2, which is the third bit up, and run that to the LED. It runs at about runs quite a bit slower, runs slower. So we know our counter's probably working. Well, we haven't hooked up 12 LEDs and waited for all 12 LEDs to blink, but I think we've got a good indication that the counter is counting. So a pretty simple test with the facilities that we have here. Again, note the program counter that we set up, the load will take priority over the increment. So if we want to play with the load function, let's just hook that up to the key, and load the PC value with 0. So if we press the button, and remember the LED had the reverse polarity, so if it's high, then it will shut the light off. If it's low, it'll turn it on. So we'll need to flip that. So basically, if we press the button, it should load that PC value while the button's pressed, and that will send out a constant to the LED and shut it off. And that did work, so we know that the load function works. We could play with it in the other sense, because if something, and it would blink when the button's not pressed because the counter's still counting, and it'll stop blinking. But how do we know we're just not resetting the counter or something? Well, if we do, or that bit's not just the wrong way, well, we can tell that by loading a value of 4 and then looking at that same bit in the same way. And if the LED does the reverse, then we know that that works. So we basically used our LED and our push button and tested the program counter, rudimentary, and yeah, we can move that across and play with higher bits and wait for the 12th bit to go and some period of time, but it's not necessary for what we're doing right now. We'll completely verify all of this at some later step, and by completely verify, I'm sure some purists out there will say, well, you never really completely verify everything, and they're probably right, but we'll verify it to our own satisfaction. But hey, while we're here, we've created a nice little 555 equivalent. Let's throw that in a new Vhdl file. So what does that look like? We might want that slow clock later, so let's just make it, but take it out of the clutter of our top level entity. That CPU 001 will be filled with wires already to hook up all the elements that go below it. And let's just reduce that down to a very simple element which takes in that 50 megahertz clock and sends out that single pulse every 12 hertz. And that looks like this code. That same library boilerplate at the top. Slow clock appears in 3 places here. The signals that we had in the higher level entity just get copied, moved up over to here, and deleted out of the top level entity, and that same function just gets moved down. So you can easily make stuff in a higher level entity and then move it down in just by picking the pieces out and moving them over to the entity you want to create in this sort of style. Sometimes it's just easier to throw something down in. So we've basically taken all of this lines of code, and at the top level it'll appear quite a bit smaller. And in fact, that's what it looks like if we instantiate it in the top and leave that same test case we had here, and it did work. So we know that that was successful. It really just boils down to these few lines here in the top level entity and gets rid of all the wires and a lot less complexity in the top. And again, we might want to use this slow clock for something we're doing later on, or you might want to use it in some debugging of the processor if you're trying to see what's going on with something and it's just going way too fast at 12.5 MIPS. It'll be handy. So in summary, what have we done? Well, we've built a program counter, and to some degree we've tested it. We saw that the counter did load, and the counter does count, and I think that's a good start to the program counter. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindy where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.